So please welcome Graeme Dandy.
Thank you, Julia. Well, this was a very big project, and I'm not going to set out to cover all the aspects of the project, and I don't really like the title of the project very much because I guess for those involved in urban water planning, you know there's not one optimal mix. It's a matter of developing what your objectives are and what the trade-offs are between those objectives, and there's a number of different efficient solutions. I want to acknowledge the co-authors of this. I'm really talking just about part of this project to do with the modelling and optimisation part, and these are the people from CSIRO, University of Adelaide, SA Water and University of South Australia who are involved in this component. Here's an outline of my presentation. I first of all want to talk about the optimal water mix framework, then talk about the development of the source model, source being the general hydrologic modelling tool, the optimisation setup, the results from the optimisation for 2013 and 2050 scenarios, and a summary. So really the aim of the project was not necessarily to produce results, but to develop this framework and demonstrate the framework. And as part of this study, it involved not only the modelling and optimisation, but also people involved in stakeholder engagement, focus groups, sociology, economics, governance issues, and also looking at demand issues. And I'm not talking about any of those today, although they're all very important. But the general framework really follows the systems framework. Do we actually have a laser pointer? Doesn't look like it. So if you follow down the left-hand side, you can see we start off identifying the goals, formulating the problem, identifying the objectives and decision variables, and then the part in the box there is the modelling of different alternatives and the optimisation part, and then at the end there's selection of preferred alternatives involving stakeholder preferences. And the focus of the study was Metropolitan Adelaide, which we've used the boundary here from the Water for Good study. Aerial photograph of Adelaide there, which is before the new stand went up at Adelaide Oval, so I'm going to prize that particular picture. And I just want to give a disclaimer that I want to emphasise that this study was about developing the framework. Although I'll present some results, obviously more work would be required to develop these to give clear guidance for policy. But I think there are some trends there, but I wouldn't want anybody to look at a particular figure on a graph and take that number as being gospel. So in terms of the source model development, now source is a hydrologic platform that's being used, really as being accepted as the hydrologic platform for Australia. And there was quite a lot of work in developing the source model. So we looked at three scenarios, basically 2013, which were current conditions, 2025 and 2050, with using 30 years of demand and rainfall variability to take into account variation. And the 2025 and 2050 scenarios actually had some climate change built in. So I think for 2050, there was an assumed 24% reduction in runoff from the local catchments. All of the demand was broken into residential and non-residential, and then the residential was broken into potable, or both of those were broken into potable and non-potable. So for the potable residential, we're looking at the kitchen, the bathroom and other indoor usage, and the non-potable we included laundry, toilet flushing and garden and outdoor uses. So here you can see a projection of the demands for 2013 up to 2050. These figures include not only the water supplied by SA Water for this region, but also water that was at the time in 2013 supplied from rainwater tanks and from stormwater harvesting and wastewater reuse. And you can see we split that into residential, non-residential, potable, non-potable, and hot and cold water for the residential potable. This is a schematic of the source model. It's a bit more complicated when you look at the details of it, but basically this shows the components of this. So basically we've got the Adelaide Hills catchments, which was simplified into three equivalent reservoirs in the north, or really the Goyder, Torrens and Onkaparinga, 3 pipelines from the Murray, the Adelaide desalination plant, the possibility of transferring water from the north to south or south to north, and 3 major demand zones with those 4 components of demand that I talked about: residential, non-residential, potable, non-potable. In addition, various stormwater schemes. In fact, I think we considered 25 equivalent stormwater schemes. Some of those were summed up from about 70 possible stormwater schemes, stormwater harvesting, and the 3 major wastewater treatment plants. And the stormwater and wastewater could be used for non-potable use in each of the zones. So, as I mentioned, the sources considered were surface water from the Mount Lofty Ranges, water from the River Murray, the desalination plant, harvested stormwater and recycled wastewater. We didn't actually model groundwater because we knew that Ocky's study was ongoing and there would be something comprehensive coming out of that. So for this particular study, we assumed a particular constant amount of groundwater being available and being used within the system. Rainwater tanks and demand management were also modelled but not included in the optimisation part of the study. As I mentioned, 3 demand zones, central, north and southern, lumped reservoirs and 25 aggregated stormwater schemes, and the 3 major wastewater treatment plants. And the main model works with a monthly time step, although the stormwater modelling was done with daily time steps and aggregated. Now, within SOURCE, there's a possibility of looking at optimisation. In fact, there's a multi-objective optimisation component, which is called InSight, which uses, for those who are interested in this area, NSGA2 as the basis. So just to think about multi-objective optimisation, here's a graph that demonstrates the idea that really when we're talking about more than one objective, we can't really talk about a true optimum solution. There's really a range of optimum solutions that are efficient in those objectives. So here, if we were considering on the vertical axis, for example, environmental impacts that we're trying to minimise, and the horizontal axis costs that we're trying to minimise, we have a lot of solutions, the grey points and the blue points, and what we want to identify are the blue solutions that we might call the non-dominated, that we call the non-dominated solutions that are the most efficient in terms of these 2 objectives. So there's no reason why we want to come up with a solution that has higher cost or environmental impact if there's one available that's better in both of those criteria. Then, of course, the choice between these different blue points becomes becomes an issue of how you value or weight those different objectives. So there's not a single optimum solution, there's a range of solutions available. In our case, we considered 4 objectives: minimisation of present value of cost over a 25-year period. That included the capital cost of new projects, but not anything that was already built, and operating cost for all systems. The total energy used over a 25-year period is the second one. The third one was the reliability of the non-potable system, percentage of time that the non-potable system met demand. And the final one was a measure of environmental impact on the Gulf, which we didn't have a lot of detail on, but we looked at the total discharge of stormwater and wastewater to the Gulf as a surrogate for environmental impact on the Gulf. We did actually look at weighting stormwater and wastewater relative to each other, but the impacts on the Gulf are primarily due to suspended sediments, which are mainly in the stormwater, and nutrients, which are mainly in the wastewater. And with quite a bit of discussion, we decided to weight the 2 equally. Now, we did have constraints. We wanted the potable system to be very reliable, and we used a minimum reliability of 99.5%. And we did have environmental flows or environmental releases from the reservoir that had to be met. The decision variables are really the maximum flow that can be drawn from the desalination plant on a monthly basis, the flows from the River Murray via the pipelines, which of the 25 stormwater schemes would be implemented, so they're either fully implemented or not, and how much the capacity of the wastewater treatment plants could be increased in terms of their recycling capacity. Now, one thing with SOURCE that we thought was a limitation, but I think turned out to be a positive, and that is we were trying to work out which mix of sources of water we should use, but source actually requires you to put some priority on the different sources. And that's a priority for the potable and the non-potable. So we've actually looked at 3 different priority sets, and that enabled us to make use of the information we got from stakeholders to set those priorities. So the first priority set we took actually came from a survey as part of the Managed Aquifer Recharge study that was carried out for Goyder. And basically the stakeholders there indicated for potable they'd prefer that Mount Lofty Ranges water was used first, second RM, River Murray, and thirdly the desalination plant. Whereas for non-potable, they'd prefer that stormwater would be used first, then harvested wastewater, then Mount Lofty Ranges, River Murray, and the desalination plant. So when we do the optimisation, we don't come up with a single solution, we come up with a set of solutions. Here we've got about 100 of them, and we're looking at these plotted in two of the objectives. Now, when I say 100, these are 100 efficient solutions of the thousands, many, many thousands of solutions that you could have. And what you see is an interesting fact that as you spend more money, you can actually reduce the total amount of energy used by going for more energy efficient solutions that actually may cost more money. But then eventually you reach a point where the energy becomes minimum and the energy and costs start to increase. And that is reflected by starting to develop new, more marginal stormwater schemes and using more wastewater harvesting, wastewater reuse. The non-potable volumetric reliability was probably a bit of a non-issue because we found that generally that reliability could be very high in the order of about 99.6% or more, although it dropped off a bit if you made use of more wastewater and stormwater towards the higher cost end of the graph here. But this was a very interesting one, probably intuitive in many ways, but it shows that if you wanted to reduce the stormwater and wastewater discharges to the coast, obviously you harvested more stormwater, you reused more wastewater, so that cost more money, so there was a definite trade-off. I got an indication, is that a few minutes to go? Or okay, I'll try not to speak too quickly, but then we looked at 2 other sets of priorities. The second one was based on operating cost, so the non-potable uses were reprioritised in terms of operating cost, and the third one came out of focus groups for this particular study where people wanted to use desalinated water ahead of the River Murray, which was an interesting indication. But these priorities don't totally dictate what you're going to use, they just come into the modelling. That's a bit of a mess, but there are 3 different colours there indicating the 3 different priority sets. The magenta or purple ones are based on cost, so you can see you get, for any energy level, you get lower cost solutions, but there are similar trade-offs, and a similar trade-off between total discharge to the Gulf and cost. So let's look at a couple of these solutions. So here I have 3 solutions. One is the minimum total cost, one is the minimum total energy, one is the minimum total discharge, and you can see that if you want to reduce the discharge to the Gulf, not surprisingly, the cost goes up quite significantly, and there is a minimum energy solution that's kind of intermediate in terms of discharge to the coast, to the Gulf. But what's of more interest in terms of these solutions is what mix of water are we actually coming up with here? Well, we find for these solutions that the Mount Lofty Ranges are supplying, this is under current conditions, about 50% of the water. The River Murray, if you want to go for a minimum cost solution, would supply about 40%. But if you wanted to reduce the discharge to the coast, you can drop that down quite a bit and supplying about 7%. Wastewater reuse going from 3% up to about 32%, supplying 32% of the demand, and greater stormwater use, but much more wastewater than stormwater, partly because it's more cost effective to do that. And the desalination plant doesn't supply very much water at all because it's fairly expensive and energy intensive. If we go to 2050, similar figures with the graphs, but if we look at the results here, there's a similar pattern. If you want to reduce the discharge to the Gulf, obviously there's greater cost involved to implement the wastewater and stormwater schemes. So there's a trade-off there. And what's the mix if we're looking at 2050? Now bear in mind this takes into account some climate change. As I mentioned, 24% reduction in runoff in the Mount Lofty ranges. You can see the Mount Lofty contribution is reduced from 50 to about 34%. River Murray about 50%, so somewhat increased. But again, if you want to reduce the discharge to the Gulf, you use less from the River Murray and implement more wastewater and more stormwater. But again, the desalination plant isn't used very much. So, in summary, we've developed a multi-objective decision-making framework for selecting water sources for major cities, so we could see this framework could be applied in other major cities. And it's been applied as an example to Metropolitan Adelaide. And that included the development of a source model in a multi-objective optimisation framework for the period up to 2050. We got out of the optimisation, you don't just get one solution, you get a range of solutions and you get an idea of what the trade-offs are between the various objectives and the different mixes and how you might vary that to achieve different objectives. The current version of source requires priorities to be set on the various water sources, but that doesn't dominate the optimisation. It really just is an input. And for the cost and energy source values used, it appears that wastewater reuse is more cost effective than stormwater harvesting out of the studies that we've got. So in concluding, the study really demonstrated the potential use of multi-objective optimisation linked to a hydrologic model as a decision support tool for developing urban water policy. Thank you.